The last main unit that you guys look at in grade 11 physics is a unit on waves. And this is a great unit in grade 11. And unfortunately, we're not in my lab, otherwise there's tons and tons of really cool things that I could show you guys. But unfortunately, we have to do it this way. But that's okay. We will do what we can. Now, waves is a really interesting unit. There's lots of really cool things we can do with it, but we're going to start by just looking at the fundamental basic idea of waves and what waves actually are, and just look at some of the basic mechanics and types of waves and stuff like that. Okay, so first things first, what is a wave in the first place? Well, the most important part about a wave by far is it is the movement of energy. And that is one of the most important parts by far. Is waves are the movement of energy, or the motion of energy from one place to another. And it's the movement of energy through what's called a medium. And of course, a medium is something that has something go through it. So probably the most common types of mediums that people think of for waves are things like, like for example, like air for sound waves, or water for like water waves. There's lots of different things that are used for mediums, but air and water are two really common ones, light waves and sound waves and lots of different things. So it's definitely the motion or movement of energy through a medium. Now, you got to be careful with this, because it's the movement of the energy. It's not the movement of the medium, which means the medium doesn't actually go anywhere. So what you'll often see as well is there's no net displacement for the medium, which doesn't mean that the medium doesn't move, but the actual medium itself doesn't actually go anywhere. For example, just take like a rope or a skipping rope or a cable or a chain, whatever you want, and you flick it and make a wave. Well, the wave moves from one end to the other, and the rope may wiggle up and down or side to side or whatever it is, but the actual rope doesn't actually go anywhere. It ends up being in the exact same place it was before, but the wave has actually moved on. So it's all about the movement of energy from one place to another, but the medium doesn't actually end up going anywhere overall. All right. And a nice place to see this is, you think about the beach or something like that, and you're standing on the beach and you're watching the water, and you think you're actually watching the water come in, but you actually aren't. You're watching the waves come in. You're watching the energy come in. But the water may move one way, but then it moves back. The water doesn't actually overall go anywhere. A nice way to easily see this is, if you're at the beach and there's like little waves in the beach, like rolling waves in the water, and somebody's like floating on an inner tube or an inflatable, like an air mattress or something like that, whatever, and they're floating out in the water. Well, when you actually watch them move, they're sort of like bobbing up and down, and that's basically what they do. If the water was actually moving, they would just come right to the shore and that's it, but they don't. Because the water, it bobs up and down, it moves up and down, but there's no net displacement. So it goes one way, then it goes back. But the energy does go all the way through. So it's kind of a weird thing to think about, but that's the way waves actually move. It's all about the movement of the energy, and the medium overall will stay in one place. Okay? So we're going to start by looking at the two main types of waves there are, and we're going to start with what most people think about a wave. And one of the most common types of waves out there is what's called a transverse wave. And this is the one that looks something like this, which is what most people are familiar with, something like that type of thing. So like an up and down type wave. Okay, so we have a transverse wave, and that's what it looks like. So we're going to use a little simulation here to sort of get an idea. So here's a transverse wave. This is what most people think of when they think about waves anyway, but here's a nice transverse wave. Okay, so you have the little white things. Those are like the particles. Those are the medium. And you can see the actual wave is moving towards the right, but the actual medium just wiggles up and down. The actual medium, the actual particles don't end up going anywhere. They just wiggle back and forth. But the energy, the actual wave itself, actually moves from one side to the other. Okay, so this is what most people think of when they think about waves anyway. And this is what's called a transverse wave. So for this one, you've got the energy moving towards the right, and you've got the particles moving up and down. And this basically defines what a transverse wave actually is. Okay, so a transverse wave is actually defined based on the motion of the two things. If you actually look at the motion of the situation, if you look at the motion of the energy and you look at the motion of the medium, the two are perpendicular to each other. So one's moving one way and one's moving perpendicular to it. All right, so they're at 90 degrees. So the two are always perpendicular to each other. And that basically defines what a transverse wave actually is. Okay, so go back to our little simulation thing. So there you go. So one's moving one way and one is moving perpendicular to it. Okay, even if we change the wave, there we go. Okay, energy is moving to the right and the wave particles are moving up and down, perpendicular. All right, so let's look at some other things with this though. Let's label some different parts. So I'm going to sort of draw a bigger one. We can label some things about a transverse wave here. So this will make it a little bit larger and look at some of the important parts. Okay, now some of the most important parts of the actual wave are like the different locations. And one of the more important locations on here is the very, very top and the very, very bottom. At the very, very top of the wave, this is what's called a crest, and the bottom part here is what's called a trough. And you may have heard of the crest of a wave or a wave cresting before, so that's the top of the wave, and the bottom part's called a trough. And the reason it's called a trough is if you actually looked at a three-dimensional wave, if you could actually see a wave in real life, and it was sort of stretched out, this bottom part here would actually look like a long trough, like an eaves trough. You know, that's why it's called a trough. So that's where the name sort of comes from. Okay, so we got the crests and we have troughs, and those are the two main parts. We got the top part, crest, bottom part is called the trough. Okay, the middle part here, right in that middle part there, sort of like the right across there, this is what is called the rest position, because that's where the material or the medium would be if this thing was at rest. So the crest is above and the trough is below the rest position, right? Now, a couple other measurements that kick in is how far it goes from that rest position. That right there, that distance right there, and that distance right there. And that's often labeled with a capital A, and that capital A stands for amplitude. So that's the amplitude of the wave, is how far it is from the rest position to the top or the bottom. Okay, and one other really, really common measurement that is used all the time is how long the wave is. And that would be, for example, we could go from here all the way across from crest to crest. You could also go from trough to trough, or one complete cycle, and that would be what's called the wavelength. And the wavelength is symbolized by the Greek letter lambda, which sort of looks like an upside down Y. It's a Greek letter. And that is the wavelength. So you got the amplitude, which is the A, and you've got the lambda, and that's the length for one complete cycle, or the wavelength. And it could be from crest to crest, it could be from trough to trough, it could be from this rest position all the way through to here like this. That would also be one wavelength. There's lots of different ways that you can actually label a wavelength. Okay, but that's your basic transverse wave. You've got crests, you've got troughs, energy is perpendicular to the medium, we've got the amplitude, and we have the wavelength. Okay, now the second most common type of wave out there is a little bit different. It's called a longitudinal wave. And this is also a really, really common form of wave. Most people don't think about it, but it is a really, really common kind of wave. And we're going to look at that one as well. Okay, now this one, we are going to look at the animation because it's a little bit harder to describe. Okay, so let's look at a longitudinal wave looks like. So we'll get this thing going here. There we go. So this is a longitudinal wave, okay, where this thing goes back and forth, and it pushes the material forward and it squishes it together, and then it pulls back and spreads it apart. So this is a longitudinal wave. And the most common longitudinal wave you can think of is sound. And you just think about this being a speaker pushing the air back and forth, because that's how sound is made. So this is what a longitudinal wave will look like. Okay, so let's look at some of the properties and descriptions of a longitudinal wave. So for a longitudinal wave, a little bit different. The motion is a little bit different. For a transverse wave, the two are perpendicular. But if you look at a longitudinal wave, if you look at the motion, the energy was going sideways and the medium was going sideways. So the two are parallel to each other. So the energy and the medium motions are parallel. Now, if we sketch this out a little bit different to draw, but we can sketch it out. There's certain areas where stuff was squished together, and then it would spread out, and then it would squish together, and then it spreads out again, and keeps on going. Now, we don't have crests and troughs for these types of waves. It's a little bit different. In the areas where it is squished together, like this, that is what's called a compression. And the parts where it's spread out, that is called a rarefaction. Okay, so the compressions are where it's squished. So that's like the higher density areas, and the rarefactions is where it's spread out. So there's lower density areas. So instead of crests and troughs, we have compressions and rarefactions. High pressure, low pressure, high density, low density. Okay, if you ever put your hand in front of a really loud speaker and you can feel it hitting you, it's those compressions hitting your hand. Okay, now we can also label a wavelength on here. So for example, here's the compression right there. There's the next compression. So that would be the wavelength from there to there. There'd be another wavelength from here to here. That would be another wavelength. You could also go from rarefaction to rarefaction. So that's where the wavelength is. Now, it's kind of rare to label amplitude on a wave like this because there's no rest position to compression and rarefaction distance. You can do amplitude if you actually look at pressure wave of it, but usually amplitude you don't label on something like this. Okay. So going back to that simulation a little bit, get it going a little bit more here. You can see it moving forward, making those compressions. It pulls back and makes the rarefactions. All right. We can even make it a little more dramatic stuff that, but we'll do some more of that stuff later on. But that's the basic idea behind a compression and refraction wave. Sometimes it's even called a compression wave, but technically called a longitudinal wave. So you have the transverse waves, which are more like up and down type wave. That's what a lot of people think of. And then we have the longitudinal waves, which are more the parallel type motion with energy and the medium moving in the same direction. But those are your two main types of waves.